Hi everyone. Today we are going to study another contention based protocol, that is the slotted Aloha. Now in our previous video when we studied pure Aloha, we saw that the performance of Aloha was not good as the number of unsuccessful transmissions were increasing exponentially with the load G. So we said that we will study an improvement or enhancement of the pure Aloha, which would be slotted Aloha. So let's look at the slotted Aloha protocol. Now basically the performance of pure Aloha can be improved by reducing the probability of collision. As we know, the main reason for the poor performance of pure Aloha protocol was that there was a higher probability of collision. In slotted Aloha, stations are allowed to transmit frames in slots only. So this is an improvement over the pure Aloha, wherein in the pure Aloha, all the stations, whenever they were ready to transmit the data, could transmit their data irrespective of the fact whether other stations were also transmitting at the same time or not. But here we have slightly improvised this pure Aloha in the slotted Aloha version. Here these stations are allowed to transmit in their slots only in their particular time slots only, and the stations cannot transmit as and when they want. So there are particular time slots and they can transmit only in those time slots. Now if more than one station transmits in the same slot, it is quite obvious that it will lead to collision. So allotting slots to stations reduces the occurrence of collision in the network system. So what we do is that in case of slotted Aloha, we allot slots to the stations so that not all the stations try to transmit during the same time slot. So this basically reduces the occurrence of collision in the network system. Now here every station has to maintain a record of the time slot, right? Because they'll be provided certain time slots and they are supposed to transmit during those time slots only. So obviously they have to maintain a record of the time slot. The process of transmission will be initiated by any station at the beginning of the time slot only, right? So any station that wishes to transmit would be allotted a particular time slot and it will then transmit the data at the beginning of the time slot only. Also, the frames are assumed to be of constant length. Now, just like in case of pure Aloha, here also we assume that the frames are all of constant length and with the same transmission time. That is, the time taken for transmission is the same for all the frames and the length of the frames is also same for all the frames. Here the frame will collide with the reference frame only if it arrives in the interval T0 to T0. So here the probability or the vulnerable time period has reduced, right? So T0, as you know, represents the time of transmission, the time at which the transmission begins, and T is the time taken for transmission. So here the vulnerable time period or the vulnerable time period is basically T0 to T0. That means the frames will collide with the reference frame only if they arrive in this particular time interval, which is T0 to T0. So the vulnerable period is reduced to T seconds long. If you have studied pure Aloha, you must be knowing that the vulnerable time interval was there 2T. Right, so definitely the vulnerable period is reduced to T seconds long in case of slotted Aloha. Now the throughput of the system S, the throughput as you know is represented by S, is equal to the total arrival rate, which is represented by G. So it is quite obvious whatever would be the total arrival rate of the frames would be the throughput of the system. So if I represent total arrival rate by G and the throughput of the system by S, then I can say that S is equal to G times the probability of successful transmission. So if P represents the probability of successful transmission, then S equals to G times P, right? So that means I can say that throughput is equal to the total arrival rate of frames into the probability of successful transmission. And what is the probability of successful transmission? The probability of successful transmission is 0 frame transmission in t seconds. As I said, t is the vulnerable time period over here. So over here, if 0 frames are transmitted during this vulnerable time period or in t seconds, then we can say that the throughput of the system S equals to G into P, where S is the throughput of the system, G is the total arrival rate of the frames, and P is the probability of successful transmission. And what is the probability of successful, what would ensure the probability of successful transmission? That there are 0 frames transmitted in the t time seconds, which would ensure no collision. Now the probability of k frames, right? K could be any number. It could be 0 frames, 1 frames, 2 frames. So the probability of k frames transmission in t seconds, which is the vulnerable time period, is given by the Poisson distribution as follows. So the probability of k frames transmission is g to the power k into e to the power minus g factorial k, right? Where k could be 0, 1, 2, 3, right? So the average load in the vulnerable interval is 1 frame time, right? So the average load, which is represented by G, is 1 frame time in the vulnerable interval. Hence the probability of 0 frames in t seconds, or in other words, the probability of 0 frames in the vulnerable time period is e to the power minus g. So in that case, I can say that the throughput S of the system is equal to G into e to the power minus g. Now, if again, just like in pure Aloha, as I had shown, if I show you in a graphical manner the relationship between the throughput S and the load of the system G, then it can be shown through the following figure. So this is the throughput of the system and this is the load of the system. So throughput versus load graph of in case of slotted Aloha looks like this. Now from the figure you can see that system is exhibiting its performance. Why? Because in case of pure Aloha, if you remember, this was 18%, right? The throughput was 18% with half the load. In this case, the throughput has improved and reached up to 36%, right? So definitely we can see that the system is exhibiting its performance. Maximum throughput that can be achieved with slotted Aloha. Okay, so the maximum throughput that you can achieve with slotted Aloha is S equals to 1 by E, which is equals to 36% approximately, which you can see here graphically also, right? So from 18% in case of pure Aloha, we have reached to 36% in case of slotted Aloha. However, you still know that with this performance, we are not able to utilize the channel or the medium in an efficient manner. 36% is still not a good percentage. So we will discuss a new protocol which is known as CSMA in the next lecture, which is carrier sense multiple access. So what is CSMA? That we will discuss in the next lecture.